this lesson, we are going to talk about reducing square roots. So when you are simplifying square roots, you are going to split your root into two numbers, okay? The first number should be a perfect square, and the second number should be a prime number or a number that is the product of prime numbers. Now, an easy way to do this is to use a factor tree. If you're not good at recognizing your perfect squares and your prime numbers, then a factor tree is the way for you to go. So let's talk about 108. If I did a factor tree for 108, I could do 2 and 54. I could do 54 as being 2 and 27. 27 is 3 times 9, and 9 is 3 times 3. So I could write that as 3 to the third times 2 to the second. Well, I know from experience that if I have even numbered exponents, those make perfect squares. Well, I have a 3 up here. So I'm going to cut one off of that because that would be the largest even number. Less than 3 would be the number less than 3, which is 2. So I'm going to use 2 of those to make a perfect square. I already have my 2 squared as being a perfect square. And then I have a 3 left over that I shaved off of here. So I still have 3 3s. I'm just using them in a way to help me solve this. So I have the square root of 3 to the second times the square root of 2 to the second times the square root of 3. I always put my perfect squares in the front, so I know that the square root of 3 squared is 3 times the square root of 2 squared is 2, and then I know that 3 is a prime number and it's going to remain under the root. Now I just multiply outside. 3 times 2 is 6. So I have 6 square roots of 3. So for 147, I know that 147 is 3 times 49. 3 is prime. 49 is 7 times 7, both of which are prime. So I have 7 to the second power times 3 to the first. Well, I already know that powers of even numbers are perfect squares. So 7 squared is a perfect square, and 3 to the first, that's a prime number. So I have my perfect square of 7 squared times the square root of 3. The square root of 7 squared is 7, and then my square root of 3, that's my prime number, will stay underneath the root. So if I do 24, 24 is 2 times 12. 2 is prime. 12 is 2 times 6. 2 is prime. And 6 is 2 times 3. So I have 2 to the third times 3 to the first. Well, I already know 3 is not going to divide by that root of 2. So I'm going to shave one off of that and use 2 of these as my perfect square. And that leaves me with a single 2 and a single 3. All right. So 2 squared is a perfect square. I'm going to put that in the front. And then I have the square root of 2 and the square root of 3. The square root of 2 squared is 2. And then I already know that 2 is a prime number and 3 is a prime number, and I can't take the square root of prime numbers. So I'm going to multiply those together. 2 times 3 is 6. When I made that statement earlier about what's left under the root should be the product of prime numbers, that's what I'm talking about. 6 is the product of 2 and 3, which are both prime numbers. Now, when you have a number on the outside, like this negative, you're just going to leave that there. All right, and you're going to do your factor tree for 80. So we have 2 times 40. 2 is prime. 40 is 2 times 20. 2 is prime. 20 is 2 times 10. 2 is prime. And 10 is 2 times 5. both of which are prime. So 2 to the 4th, I have 4 of those, times 5 to the 1st. So 2 to the 4th, I already know that because this has an even power, this is a perfect square. And then I have 5 to the 1st, this is prime, so it's going to be my number that stays under the root. So I have the square root of 2 to the 4th times the square root of 5. Now remember, when you take the square root, you're really just taking that exponent and dividing it by that root number out here. So I have a negative out front, and then the square root of 2 to the 4th would be 2 to the 4 divided by 2, which is 2. And then 5 is my prime number that stays under the root. So 2 squared is 4, so I have negative 4 square roots of 5. So number 5, we have 75. That would be 3 and 25. Don't know why I was thinking 15. 3 times 25. 3 is prime. 25 is 5 times 5, both of which are prime. So I have 5 to the 2nd times 3 to the 1st. I already know because this has an even numbered exponent. I have 2 of them. That's a perfect square. And then 3 is my prime number. So I have the square root of 5 squared times the square root of 3. The square root of 5 squared is 5. And then my prime number is left under the root. So I have 5 square roots of 3. All right, so for 96, I know that 96 is 6 times 16. 6 is 2 times 3. 16 is 2 times 8. 8 is 2 times 4. And 4 is 2 times 2. So I have 1, 2, 3, 4, 5 2s and a single 3. Well, I already know that I can't take 2 to the 5th and root that, so I'm going to shave 1 off of that, and that would give me 2 to the 4th. I have a 2 left over, and then I also have that prime number of 3. So 2 to the 4th is going to be my perfect square. And then I have the square root of 2 and the square root of 3. The square root of 2 to the 4th is 2 to the 4 divided by 2, which would be 2. And then I already know that I have this prime number and this prime number left, so I multiply those to get 6. And 2 squared is 4, so I have 4 square roots of 6. All right, now we're going to add in some variables. So when you do this, I want you to take and separate the coefficient from the variable. So move the number and the variable. So we're going to multiply those separate, and we're going to think about them separate. So 9 is a perfect square. I don't need to do a factor tree for 9 because it's a perfect square. All right, but I know that this x to the 3rd, I can't take 3 and divide it by 2. So I'm going to do what I do with the numbers, and I'm going to split this into 2 where I shave 1 off of this because that would be the largest even number that's less than 3, which leaves me with 1 left over. You should have no more than 1 variable left over in there. All right, so my perfect squares are the square root of 9 and the square root of x squared. The square root of 9 is 3. The square root of x squared is x. And then I have my x to the 1st left inside. All right, let's do the same thing with number 8. So I have the square root of 25 and the square root of x to the 5th. Well, I already know that 25 is a perfect square, so I don't need to do a factor tree for that. So I'm going to leave that alone until I'm ready to square root everything. I cannot divide 5 by 2. So I shave 1 off of that, which leaves me with 4, and then 1 is left over. That gives me a total of x to the 5th, okay? And then my perfect squares are x to the 4th and 25, so the square root of 25 is 5. The square root of x to the 4th is x to the 2nd. Remember, you're just taking 4, dividing that by the root of 2, and then you have your x to the 1st left underneath the root. All right, number 9. Now, we did the square root of 75 on a previous problem, so I'm not going to do a factor tree for that. I'm just going, we did it on number 5, so maybe put up here reference number 5 if you need to. And then we also have the square root of n to the 5th. So I already know that for 75 we used 5 to the 2nd and 3. And then I can't divide 5 by 2, so I shave one off of that, and I get n to the 4th times the square root of n. Now my perfect squares are the square root of 5 squared and the square root of n to the 4th. So I'm going to do those first. The square root of 5 squared is 5, and the square root of n to the 4th is n to the 2nd. And then whatever is left, okay, your prime parts, the 3 and the n to the 1st, are going to get multiplied together underneath one root. All right, 162 is not a perfect square, so I am going to do a factor tree for that. So I know that 162 is 2 times 81. 81 is 9 times 9. 9 is 3 times 3. So I have 4 3s and a 2. This makes me have a perfect square, and this is my prime number. So I have the square root of 3 to the 4th times the square root of 2. And then I have my square root of x to the 4th, and x to the 4th is a perfect square because 4 in that exponent will divide by 2. So my perfect squares are 3 to the 4th and x to the 4th. So the square root of 3 to the 4th is 3 to the 2nd, because remember you're taking that exponent of 4, dividing it by that root of 2. The square root of x to the 4th is x to the 2nd. And then always have your prime number under the root left at the back. So square root of 2. And then I need to simplify this. 3 squared is 9. So I have 9x squared times the square root of 2. All right, 180. All right, 180. 180, I can do 5 times 36. 5 is prime. 36 is 6 times 6. And 6 is 2 times 3. So I have 2 to the 2nd, 3 to the 2nd, and a 5. So 2 squared is a perfect square, 3 squared is a perfect square, and then I have my prime number, 5 to the 1st, so I have the square root of 2 squared times the square root of 3 squared times the square root of 5. Then I see that I have x to the 9th. I know 9 does not divide by 3, or divide by 2. It does divide by 3, but we're not doing cube roots. So we're going to shave one off and use x to the 8th, which leaves one of those x's left over. So my perfect squares are 2 squared, 3 squared, and x to the 8th. The square root of 2 squared is 2 times the square root of 3 squared is 3 times the square root of x to the 8th is x to the 4th. Remember, 8 divided by 2. And then underneath I have a 5 times an x, so 5x, and then simplify. 2 times 3 gives us 6x to the 4th, square root of 5x. All right, I already know 36 is a perfect square, so I don't need a factor tree for 36. And also x squared is a perfect square, so the square root of 36 is 6, and the square root of x squared is x. All right, so let's talk about dividing. Now, you can reduce numbers that are under a root, but sometimes it's not helpful to do that in the beginning. Sometimes when you're taking the root of something, if they're perfect squares and they reduce, you might want to, take the perfect squares first and then reduce. So if you look at number 5, we have 15 over 64. I can split this and do the square root of the numerator over the square root of the denominator. Now I know that the denominator is a perfect square. So I'm going to go ahead and take the square root of 64, and that's 8. Now 15, if I try to split 15 up, that's 3 times 5. And those are both prime numbers. So I can't reduce the square root of 15. So therefore, I am completely done with this problem. All right, so if I do the square root of 81 over the square root of x squared, those are both perfect squares. The square root of 81 is 9, and the square root of x squared is x. All right, number 15, I'm going to do the square root of 11 over the square root of 36. I see that that bottom square root of 36 is a perfect square. So I'm going to go ahead and take care of that. So I have square root of 11 over 6. Now 11 is a prime number, so we can't reduce the square root of 11. So we will leave it as is. All right, number 16, I'm going to take the square root of 144, which is a perfect square, over the square root of n squared, which is also a perfect square. So the square root of 144 is 12, and the square root of n squared is n. All right, 17 is also perfect square over perfect square. So I square root the top. The square root of 36 is 6, and the square root of z squared is z. All right, on 18, we're throwing in a coefficient and a variable. So the 4 is a perfect square, and x squared is a perfect square, and 64 is a perfect square. So we'll square root all of them. Square root of 4 is 2, square root of x squared is x, and square root of 64 is 8. But I am not done because I can reduce this. 2 over 8 will reduce to 1 over 4. So this would just be x over 4. All right, number 19. These are already split, and I can see that 6 is not a perfect square, and if I try to split 6, I just get 2 times 3, so it's the product of two prime numbers, and 2 is also a prime number. But, you know, something you're going to learn is we typically don't leave roots in the bottom of your fractions. So I can take this 6, since it's underneath this square root, and I can divide it by 2 because it's under the square root. So I really could think of it like this. 2 times the square root of 6 over 2, which would be 3. So this would be 2 times the square root of 3. You can also say 2 goes into 6 3 times and have your 2 square roots of 3 there. Either way, it works like that. All right, now I do know that 81 is a perfect square and 4 is a perfect square, so I get 9 over 2.